Okay, so hello, class. So we're going to talk about a kind of a new topic, or well, it's related to what we've been talking about with Navier-Stokes, the Navier-Stokes equations. So I pretty much pulled out a rabbit out of the hat in those recent notes on Navier-Stokes and talked about a viscous force term that we added, but I didn't show you how or where that came from. So that's going to be the point of this lecture or this video, but we're going to have to go through walk our way up to that point. So this is the point of that, just to get you up to speed with how that viscous force term is derived and how it's implemented in Navier-Stokes. So to start off with, there are two types of forces that act on a fluid. So you can imagine water or air or fluids, and you can have either body forces, which is a type of force that acts on all parts of a fluid inside and out. That would be something like gravity, as opposed to surface forces that act along a fluid surface, say shear stresses or viscous forces, things like that, pressure forces. They don't act inside, but they act along the surface, along a surface of a fluid. And so we've already derived, though, that pressure force contribution in class, in addition to the gravity terms and other terms. So let's derive now the viscosity term as the other surface force to those equations. Now, I just want to iterate that, say that in atmospheres, we will basically in atmospheres, most atmospheric problems don't really, at least the large scale ones, don't really care much about viscosity. This is really more important for atmospheric surface interactions. Say you have flow over a mountain or something, and you have to you really care about the small scale interaction between, say, the air and the uh, hill that it's flowing over, because you have viscosity effects that can slow down and cause friction with the air, surrounding air. So that's what that viscosity component is for. And it's also for various engineering problems. And in fact, some of the simple problems we'll be doing in this class will incorporate viscosity so that you can understand where it comes from. So let's get right to it. So the first thing we want to mention here is that there is a stress vector. And the stress vector is like a viscous force. It's usually written as a stress force term, which is the stress vector, which is a pressure. So it's in pascals and SI units multiplied by some area. So uh, if you can imagine, uh, here's the basically you have a area of some sort, dA of a fluent element, and then on top of that, you have the some sort of stress vector, sigma, right? So over that area, and since sigma, and I'll put a bar here because it's a vector, that stress vector is a pressure times the infinitesimal area that pressure force is acting on, like a viscous force, for instance. That'll give you the actual force, right? Because force is pressure times area. And so then you sum it, uh, all those little dAs with all their own little sigmas, right? Sigma 1, sigma 2, dA2, and so on and so forth. You sum that up over this integral, the surface integral, and you get then the total surface, right? You get the total surface force along that surface. And we can see that more clearly here, for instance. So here's that surface, right? Um, And here's that element dA, infinitesimal surface area dA. And there's that stress vector that's oriented somehow. But but then the normal, it has no reason, there's no reason for the force that's acting along that infinitesimal element to be oriented along the same direction as the normal. So the normal to the surface, which is perpendicular to that infinitesimal element, could very well be, almost always is, oriented differently than what the pressure force is doing. So you really need to account for, if you're trying to account for the stress vector's orientation, doing it to respect to the outward normal is kind of the simple way to do it. And this is where really the stress vector comes in, that I'm going to denote as sigma, but with these double arrows. So that's what the stress tensor is. We'll talk about now what that means. So another way to see this is that that stress vector that we talked about earlier is equal to the stress tensor times the outward unit normal. So essentially what you have here is that the stress tensor encodes information from both the stress vector and the normal. It has that information already there. So it already tells you something about the uh, the magnitude and the location of that stress force. So that's what makes it a second order tensors, because it contains two things, the stress vector and the outward unit normal. Uh, so, but in the terminology of tensors, say something like velocity, they're like first order vectors. They just have uh, uh, one vector that they're dealing with. The stress vector has basically, the stress tensor has two vectors with it, right? The stress vector itself and the outward unit normal. That's what makes it a second order tensor. But then how do we actually define what this tensor is? Well, let's look at it, right? So in 3D, this is what it looks like. It's essentially a 3 by 3 matrix, right? Where we have the sigma bars. Again, those are your stress forces. And there's subscripts for each of these, where the first element is essentially the face that the stress force is acting on, and the second subscript is the direction that stress force is acting on. So on the first row, and I think we'll see that clear on this slide, if you look at this diagram, and by the way, this diagram, all these things here, right? Um, So all of these guys here should uh, have bars over them, right? So yeah, don't be fooled. These are all bars, right? So these should all have bars, right? And so I just want to, because these are all vectors. And the thing is that, let's look at this. So we've got the sigma. So we've got, this is the X face, right? This right here is the X face. This is the Y face. And then this is the Z face. And so you have these vectors, right? For instance, sigma XX is saying, here's the first subscript tells you it's working on the X face, but in the X direction. This sigma XZ means that it's working on the X face, but in the Z direction. Sigma XY is it's working the X face, but the Y direction. Sigma YX means, okay, now we're on the pink Y face, but it's in the X direction, and so on and so forth. And that's how you fill up this entire tensor, right? This matrix. That's how it works. You have the all the X face things on the first row, and then everything working on the Y face in the second row, and then everything working on the Z face in the third row. Right. So that's the terminology or the convention of writing a tensor, the stress tensor. So again, this is what we're looking at here. Uh, you have the stress tensor sigma with the two arrows is just sigma with the first subscript meaning the orientation of the surface, and the second subscript is the direction of the force. So now that we understand tensors and the stress tensor, there's another important piece of the puzzle to get at the viscous force. So back in many a few hundred years ago, Isaac Newton had an idea of how shear stresses work, and basically shear stresses are forces that are applied parallel to a surface, right? That they shear along the surface, and this is going to be related to viscosity, as we'll see in a second. But the thing is, Newton hadn't done this by himself. He had an idea, but it wasn't until Stokes that he really wrote down the equations. He wrote it in a 3D format that I'll show in the next slide or two. So he really codified it, and then you had other pioneers, Puzel, Navier, Saint Venant, Hagen, Bingham. They tested and verified that this was an accurate equation. So there's an experimentally verified linear relationship between shear stresses and strain. Um, so this is what it is. If you assume this equation tau is shear stress, we'll just use tau. It's just another like pressure type term, but we'll use tau instead of sigma for shear stress for the purposes of this video. But this form assumes, though, that the flow is incompressible. So again, you've got the divergence of the velocity. Del dot U is zero in this case. Normally, the full version of this expression, this relationship, has an extra term, but that goes away because del dot U equals zero. In our case, that simplifies things. But essentially, what you have here is this term called the dynamic viscosity, which is a proportionality constant that relates the shear stress and something called the strain rate. It's basically just the gradient of the velocity in the y direction, assuming you have flow going in the, like say, the x direction. That's all it is. And when you look at the units, meters per second divided by meters, you get per second. And this is what's called a strain rate. And this mu, the dynamic viscosity, is just the proportionality constant between the strain rate and the shear stress. And as I said before, this has been experimentally verified. And so here it is here. Here's a plot of for different cases, the shear stress and strain relationship. So you can plot shear stress versus strain for different materials and different conditions and temperatures and find out that they lie along a straight line. So it's a constant. The slope of this is mu, right? That is the dynamic viscosity. By definition, it's the slope between it's a line that you get, right? This is basically tau equals mu du dy is what? It's just the equation of a line. Y equals mx plus b, where b is zero. That's all it is. And so the way to think about this is that viscosity then is a measure of the resistance to fluid flow. And so, for instance, pancake syrup is more viscous than water, so it has a higher viscosity. And that dynamic viscosity mu is just the constant of proportionality or slope between shear stresses and strain rates, as we see in this figure here. So you have a fluid between two plates, and the velocity at the surface at the fixed plate is zero, and then you have a moving plate above uh, at some free stream velocity. But then there's a gradient here between the bottom plate and the low plate, the high plate, where the fluid gets faster and faster. That gradient in the y direction, the rate at which the velocity changes with y, or the y direction in this case, that is the strain rate, du dy. And if you know then the dynamic viscosity, you know the shear stress. So let's put that there. So let's take this on further though. So we're remembering your math definition of divergence, right? So this is, the nabla here term is just the sum of the partials with respect to x, y, and z. So you can extend shear stress to 3D in tensor form like this, right? So instead of just du dy, you have all of this. When you look at this and you look at your definition of divergence, isn't that just this? It's mu dot del u by definition, right? So this is another way that you can write uh, Newton's equation here. It's just mu times del u, right? Nabla times u, where I've made u bold because it's a vector, right? So that's why that's bolded there. And so this is another way to write vector, right? But I made that bold to signify that it is. So if we continue this though, now we have the components, right, to derive the viscosity term to Navier-Stokes. We've learned about stress tensors. We've learned about Newton's shear stress kind of law, the linear relationship between strain rates and shear stresses. And our goal is to derive the viscosity term. So if we look back at this box, right, the shear, the stress tensor box, and looked at the stresses that are acting on that box from all directions, but we just want to look at the net force in the x direction along the x face, for instance. Well, there are three components to that. You've got to worry about not just sigma xx, which is the pressure force along the x face in the x direction, but there's also a pressure force on the y face in the x direction and a pressure force on the z face in the x direction. And we want to then compute all of those and add those together. So we'll do that. So let's look at sigma xx, which by the way, all these have bars, right? They're all vectors, right? So you have sigma xx uh, uh, x minus sigma x plus dx. So you're looking at some infinitesimal uh, distance along the x direction and getting the net force along it over the dy dz, right? So that's the area along the x face, right? You've got uh, dz, dz dy, right? Some infinitesimal area is going to be approximately equal to this, right? Because if you look at this, this is essentially the same thing. Uh, if you take derivative of sigma xx over dx times dx dy dz, it's the same thing as the left-hand side, right? You have a dx here and here. So you can see that this term here is essentially the same as that guy there, right? And you have a negative because you have x minus x plus dx here. So, but let's get this in terms of force per unit volume. So we'll divide this by dx dy dz, which is the volume, right? And then you get this. So the force over along the x face is just negative d sigma xx over dx. You see that, right? So then let's get the other two. So we got this guy. Now we can get let's do the same thing for sigma zx and sigma yx. So repeating for the y and z faces in the x direction, you have a similar thing, right? You still have the same thing here. X plus dx, except that your subscripts are now acting this the x component in the y face and the x component in the z face, but you get the same sorts of expressions here, right? So they're all looking similar. And then you add them together. So you have three partial derivatives in the x, y, and z directions that you add together. Does that look familiar? It's just a divergence, right? So if you sum, the result is summing all forces in the x direction is just a divergence of the stress tensor. So it's just del dot t. So I just changed where I replaced, because now we're instead of using a generic sigma stress term, let's just apply it to shear stress. So I just substituted sigma for tau, and let's say, okay, we're going to apply this methodology to shear stresses. So I just changed my sigmas here to taus, right? To taus instead. And so if you look at this, it's just del dot T. That's all this is. The summation of all the forces in the x direction is just del dot T. It's just the divergence of the stress tensor. So so then you have this. Tau is then mu dot del U. That's all that is, right? That's what we defined before, but this is what we define now. So now what we can do is take this that we've derived earlier and plug it here for tau, right? And see what we get here. So you have now del dot tau, which is mu dot del U, which is what we had derived a few slides back here, right? And guess what? Now this is starting to look like that term that we got here, right? So now you've got mu nabla squared dot U. Because mu is just a constant that you can pull that out. So this is really your viscous stress term for incompressible flow. But we're not quite there yet. We're almost there. So remember, these are force per unit volume units, right? But if you divide this by density, guess what you get? You got, um, mass here, mass, volume, and then, those cancel, the volumes canceling. Now you've got force per unit mass, and that's acceleration, which is exactly the correct units for Navier-Stokes. So this is what you got here. You just need to divide this by rho, and you get the right and plug this. And this is exactly what we're using in our notes and in the other set of notes. It's just this mu over rho del squared dot U. Now, if you really wanted to get complicated, well, not complicated, there's actually another. This is the dynamic viscosity, but if as we talked about back here, right? This is the dynamic viscosity, the mu term. But some people like to define this new, that's the kinematic viscosity. Some people like to make a whole new term out of this constant, but we don't have to do that in this class. We don't have any need of using nu or the kinematic viscosity. Just writing this in terms of the dynamic viscosity over rho is enough. So I hope with this derivation, this discussion, this clarifies where this viscous term comes from. And so if you have any further questions, I'd be glad to take them in class. And I will see you then.